Myself is Dr. C. Keshavulu, Associate Professor, Department of Physics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss about the different types of oxide glass systems. Today is my topic of the title is the different types of oxide glass systems. So last and previous session we discussed on thermodynamic and structural properties of lanthanide doped glasses. In this topic, last session we discussed among the thermodynamic glasses formation, glass network formers and modifiers, structural features of glass, lanthanide doped glasses, variation with the bond nature, variation with the ligand energy. These are discussed in the last session. So today we are going to discuss about the different types of oxide glass systems. So oxide-based glass system, they are classified into 5 types. Borate glasses, B2O5, boron trioxide glasses. This is glass former of the borate glasses. Second one is phosphate glasses, P2O5, phosphorus pentoxide. This is phosphate glasses, basically oxide glasses. Third one is silicate glasses, SiO2, silicon dioxide glasses. Next, fourth one is tellurite glasses, tellurium oxide glasses. Last one is germanate glasses, germanium oxide, GeO2 glasses. So these are the very prominent oxide-based glasses. First one is borate, phosphate, silicate, tellurite, germate. So we are going to discuss about each and every glass formers. First, we are going to discuss about the borate glasses, B2O3 glasses. So oxide-based glasses, this is the first one is borate glasses, B2O3, boron trioxide. So borate glasses form one of the best families among the oxide glasses, which clearly shows the relationship between the glass structure and physical properties. From the scientific point of view, an interesting characteristic of the borate glasses is the appearance of changes in its structural properties when alkaline and alkali earth cations are introduced. So here main structural properties when alkaline and alkali earth. Alkaline materials means lithium, sodium, phosphorus, potassium. These are the alkaline earth materials is calcium, beryllium, barium, magnesium. These are the alkali earth materials. These are the second group elements. These are whenever adding into the borate glasses, what structural properties, how it will be changes. We are going to discuss about in this phenomenon. So this effect is known as the boric oxide anomaly. This is explained by continuous changes of boron contribution from 3 or 4 oxygens. So in our borate glasses, B2O3 glass system, we are how to get oxide glasses, how it will be, coordination will be takes place in the boron network. That we are going to discuss about. So here, however, according to Krogh-Moore theory, this is one of the theory of the Krogh-Moore theory, the structure of borate glasses is not random distribution of boron trioxide, that is triangle, as boron tetrahedral, that means BO4, tetrahedral symmetry. So boron trioxide at the same time boron tetrahedral, how this crystal structure will be changes. But the gathering of these units to form a well-defined stable borate group such as diborate, triborate, tetraborate, etc. This kind of, whenever oxide glasses will be into interaction with the boron, it will form the different kind of structures, diborate structure, triborate structure, tetraborate structure, and different kind of structures that constitute the random and stable 3-dimensional network. These are comes from the 3-dimensional network systems. Next, with the addition of lead oxide, heavy metal oxide. Lead oxide is one of the heavy metal oxide. Lead oxide and boron trioxide and boron tetraoxide conversion takes place, resulting in the conversion of boraxyl rings to pentaborate groups. So this is the conversion of the boraxyl rings to pentaborate groups. Different kind of oxide groups combined with the boron, it will be formed the different kind of boraxyl groups. That are the lead oxide, that is a heavy metal oxide adding into the boron network. At that time, it will express the different kind of structures. That is conversion of boraxyl rings to the pentaborate groups. These are different kind of borate groups. Next, coming to the borate glasses exhibit many interesting structural variations with the temperature, pressure, and composition. So this is a very important parameter. So borate glasses exhibit many interesting structural variations with temperature, pressure, and composition. B2O3, boron trioxide, is the basic network forming oxide of borate glasses. So if borate glasses means basic glass former is boron trioxide or B2O5, boron trioxide or pentoxide. These are the important glass former of the borate glasses. The structure of vitreous B2O3 has been investigated by using X-ray diffraction. If you want to, after adding of boron network into the oxide based glasses, we can study the how structure will be there. We are going to discuss about the by using the XRD diffraction. That means X-ray diffraction we have to using the instrument, and we have to go to study the how borate structure will be looks like. So we are going to do the by using the XRD diffraction. All XRD results indicate that boron is surrounded by the three equidistant oxygens forming a regular triangle. This is very important. All XRD, if you are study the XRD graph, we can know the each and every boron will be occupied with the 3 or 4 oxygens. That is mainly 3 equivalent distance oxygen forming the regular triangle. That is a very important thing. So by using the XRD diffraction profile, we can see the how that boron will be surrounded by the 3 equidistant oxygens forming a regular triangle boron network systems. The average boron oxygen distance, say each and every boron and oxygen distance should be in the order of 1.37 angstrom to 1.39 angstrom in between each and every boron to oxygen. The interatomic distance, that is average boron oxygen distance, should be in the range of 1.37 angstrom to 1.39 angstroms. This is angstroms is 10 power of minus 10 meters. So each oxygen is connected by 2 borons. So here each oxygen should be connected with 2 borons. That is B2O3. So B2 means there is 2 borons and 3 oxygen. So each and every boron should be connected with 2 borons. So each oxygen is be connected by 2 borons. That is the boron network. So coming to the borate glasses are being used for technological applications such as high refractive index, rare earth borates, lead borate glasses in a plasma soldering, sodium resistance, aluminum borate glasses used in sodium discharge lamps. These are different kind of applications of the borate glasses. They are using plasma soldering, sodium resistance, aluminum borate glass using for the sodium discharge lamps. These are the different kind of applications for the borate glasses. Next, nuclear magnetic resonance (NMR). Nuclear magnetic resonance data of silver and Bray et al. Both are we confirmed the 3 coordinated structure of boron in B2O3 glasses. That means borate structure will be coordinated with 3 oxygens. That is why 3 coordinate structure of boron in B2O3 glass system. So the BO3 triangle, boron trioxide triangles like the silicon oxide, silicon tetrahedral means 4 oxygens. Silicon will combined with 4 oxygens. It will are interlinked to form a continuous 3-dimensional network, but the structure of B2O3 is more complex than that found in silicon dioxide. So that is the boron dioxide is more complex than the silicon dioxide. SiO2, silicate glasses and borate glasses. These are the network structure compared to borate and silicate. So borate is the more complex than that of the silicon oxide, the silicate glasses. These are the important glass formers, borate and silicates. Next, coming to the, it has been concluded that planar B3O6 boraxyl groups are present in vitreous boron trioxide. So this structure we can see in the figure 1. Next slide we can see the structure of the boraxyl groups. The Raman spectrum of vitreous B2O3 and crystalline B2O3 are quite different. If you see the Raman spectrum, if you analyze the borate structure by using the Raman analysis, you can see the how crystal structure B looks like B2O3 as well as B2O3. How structure will be looks like in the vitreous B2O3 and crystalline. That means without non-crystalline B2O3 and crystalline B2O3. How this structure will be looks like. That is, both will be not similar. It will be quite different. When I was studying by using the Raman spectral analysis. The Raman spectral analysis, we can study the non-crystalline borate and crystalline borate. Both are quite different structures. In crystalline B2O3, the boraxyl rings are absent and it consists of chain of BO3 triangles. So it will be boraxyl rings will be absent. At the same time, it consists of a chain of boron trioxide triangles. So Krogme et al. Yes, given the detailed review of the structure of B2O3 glass. You see in this paper cited by the Krogme et al. So in that paper, we can see the detailed review of the structure of B2O3 class systems. So Bray and Silver have reviewed the NMR data in boarded class systems, B2O3 class system. After that, previously the reference cited number 3 is Roma et al. Detailed overview of the structure of boarded system class systems he discussed. At the same time, after that, by using the NMR data, um, Bray and Silver both they reviewed the NMR data in boarded class systems. Finally, the structural variations that takes place in boarded classes B2O3 with the addition of alkali oxides are quite different compared to silicate classes. If you are adding the boarded classes, adding with the alkali oxides, the addition of alkali oxides, alkali elements or alkali metals is the lithium, sodium, potassium. These are adding with the boarded class system. It will be quite different if you compare to silicate glasses. SiO2. Silicates means SiO2. If you adding in silicon dioxide glasses, adding addition of alkali oxide glass means at that time it structure will be both will be different because bored network will be glass formers will be different because first one is bored glass system, other one is silicate glass system. Whenever adding of the alkali oxide glasses, both structures will be quite different. Next, coming to the bored glass system, how the boraxyl group will be looks like. With the addition of alkali oxides to B2O3, conversion of BO3 units to tetrahedral. So the B2O3 will be formed, conversion it will be formed first BO3, boron trioxide units. After that it will be converted into BO4 units, that means tetrahedral boron groups. It takes place without the creation of non-bridging oxygen, NBO, that means non-bridging oxygens. Without creation of non-bridging oxygens, we can form the boraxyl groups will be BO3 and as well as BO4 units. From the X-ray diffraction study of a series of alkali bored classes, Bisco and Warner et al. They are discovered they were the first to observe the evidence of this change in boron coordination. How the boron coordination will be changed. Here see this is schematic model for the boraxyl group which are linked by said oxygen in the B2O3 classes. See here B boron will be coordinated with sharing of 3 oxygens. See, each and every boron will be oxide with 3 oxygen. 1, 2, 3. Here also see B, 1, 2, 3. Here P oxygen, 1, 2, 3. So, each and every boron will be coordinated with 3 oxygens. 3 oxygen, that is B2O3. Here also same structure. This is the schematic model of the boraxyl group structure. Next, coming to the different kind of bored glass systems. First figure, see here, this is boraxyl group. Second one is pentaborate. Here boraxyl group B, 2 B borons will be 3. 1, 2, 3. Here pentaborates. Here 1, 2, 3, 4, 5. So here 5 pentaborates. Here metaborate rings. This is diborate ring. This is pyroborates. This metaborate chain. This is metaborate chain. Sequentially the chain is like a chain type will be metaborate chain. This is a tetraborate structure. This is orthoborate. This is triborate. These are the different kind of structural groups present in the alkali borate classes. So here the incorporation of a second BO4 tetrahedral into a pentaborate group system in the formation of a pentaborate group at higher content of alkali oxides, the non-bridging oxygens present in the form of orthoborates, pyroborates, and ring and chain type metaborates. These are the different kind of borate glass systems. The different structural groups that are present in alkali classes that are given in the figure. So these are the different boraxyl groups. Boraxyl groups is classified into boraxyl pentaborate group, next metaborate ring type, next diborate, next pyroborate, metaborate looks like a chain structure, next tetraborate, next orthoborate, next triborate. These are the different kind of borate glass systems. So this is structural groups present in the alkali borate glasses. Next, coming to the phosphate glasses. This is B2O5. First we are discussing the borate glasses. That is glass former is B2O3. Now we are going to discuss about the phosphate based glasses. These are the one of the oxide based glasses. Recently, phosphate glasses have been developed for a variety of applications due to their unique properties. Here, this is the very important unique properties such as low dispersion, next relatively high refractive index. Phosphate glasses, if compared to borate glasses, phosphate glasses having the high refractive index. refractive index will be linear refractive index will be very high, at the same time low dispersion. So low dispersion, etc. compared to the borate and telluride glasses. So these are the unique properties. If we compare to borate glasses and telluride glasses, phosphate glasses having the two important unique properties, that is a low dispersion, at the same time high refractive index. Compared to borate glasses and telluride glasses, phosphate glasses having the low dispersion, at the same time high refractive indices. The second one is the presence of P2O, phosphorus pentoxide, extend the ultraviolet UV region and reduce the infrared transmission. So this presence of phosphate glasses, so ultraviolet region will be reduces and the infrared transmission. So they extend the ultraviolet region. So UV region will be extended in the presence of phosphate glasses. At the same time, reduce the infrared region. Infrared region will be near infrared and mid infrared region will be reduced whenever adding the phosphate based glasses. That is shows the one. Next one is the data shows the potassium oxide K2O is the best modifier and aluminum oxide content should be minimized because of its adverse effect on the emission cross section. So emission cross section is very important in phosphate glasses. Whenever adding the phosphorus, adding with the addition of potassium oxide K2O5 at the same time aluminum oxide. These are the two important modifiers whenever adding to the P2O5 glass network. At that time the emission cross section will be minimized. However, some aluminum oxide, that aluminum oxide concentration should be equal or less than 12.5 mole percentage must be added as it increases the working range of the glass and improves the mechanical strength, reduce the tendency for unmixing and chemical resistance, increase the diffusion coefficient of alkali metal ions. Whenever adding the alkali metal ions, so whenever adding the phosphate glasses with aluminum oxide, this is one of the best modifier of the aluminum oxide. Whenever adding to the phosphorus pentoxide, it will be increase the working range of the glass and improves the mechanical strength. So whenever adding the aluminum oxide into the phosphate glasses, it will be increase or improve the mechanical strength and reduce the tendency for unmixing the chemical resistance. This is a very important property in the phosphate glasses. Whenever adding the aluminum oxide, it will improve the mechanical strength very strongly. So this is the very important modifier in the phosphate glasses. Next, coming to the potassium oxide act and viscosity to length the glass. Viscosity means the system fluid nature. So, however, using potassium oxide as the only modifier is not practical. So, each manufacturer has used a group 2 modifiers. That is group 2 modifiers. That is a barium oxide. In the case of LHG8, this is the solid state laser glass systems. LHG8. This is a commercial laser glass system. That is phosphate based laser glass system, LHG8, and magnesium oxide for the LG770. These are the two are the commercial phosphate solid state laser systems, LHG8 and LG770. LHG8, the glass is mainly added with the barium oxide. In this glass, mainly modifier is added is the barium oxide. This is one of the laser based phosphate glasses. Second one is magnesium oxide based LG770. These are the one of the commercial phosphate laser glass systems. These are the two important commercial laser glass system. One is LHG8, that is mainly modifier is barium oxide. Other one is LG770 is modifier is used is magnesium oxide. These are the two important solid state laser phosphate based glass systems. In the present glass network, intermediate aluminum oxide was added into phosphate glasses to increase their inherent mechanical strength. The charge compensation of trivalent aluminum and pentavalent phosphorus in tetrahedral coordination occurs when aluminum oxide are introduced into phosphate glasses. Here, whenever aluminum oxide introduced into phosphate glasses, it will be increase the automatically mechanical strength. That is very important. The second one is potassium oxide K2O was selected as a major glass network modifier due to its relatively low thermal expansion. Here, very important is low thermal expansion, high thermal conductivity, acceptable thermo-optical performance. That is why this phosphate glasses is mainly used to improve the optical performance as well as high emission cross section. Whenever the each and every glass laser system emission cross section should be more means should be one of the best glass former. So in the case of phosphate glasses is the one of the best laser glass system whenever adding of phosphorus doped with potassium oxide K2O. Whenever adding the K2 oxide into the P2O5, at that time it will be automatically it will improve the low thermal expansion, high thermal conductivity as well as thermo-optical performance. Whenever thermo-optical performance increases, automatically emission cross section should be more. So this is one of the important parameter in the laser glass system, emission cross section. So in phosphate glasses, it should be more. Whenever adding the potassium oxide K2O was whenever adding in the phosphate glasses, automatically optical performance should be more. At the same time, emission cross section should be more. So barium oxide component favors the mechanical properties that are important for fiber production. The optical fiber glass system, we can adding the modified is a barium oxide. Whenever barium oxide component favors the mechanical properties that are important for the optical fiber production. If you draw the optical fibers by using the phosphate glasses, you should have the barium oxide because barium oxide is having the mechanical properties more in that barium oxide glasses. It gives the mechanical strength more to the phosphate glasses. So that is why we can use for this barium oxide based phosphate glasses for fiber production, fiber fabrication and optical fiber synthesis. We can use the barium oxide is one of the best modifier to the phosphate glass systems. Next one is alkali and alkali earth fluorides such as potassium fluoride KF, strontium fluoride SrF2, magnesium fluoride MgF2, barium fluoride BaF2, and aluminum fluoride. They are used as a network modifiers in fluorophosphates because these are the fluoride oxides and also fluorides. We are adding with the fluorides, potassium fluoride, strontium fluoride, magnesium fluoride, barium fluoride, aluminum. Whenever adding the fluorides into the phosphate glasses, it will be known as fluorophosphate glasses as they prevent the glasses from devitrification and play important role in improving the structure, thermal properties and reducing OH bonds. Whenever adding the fluoride content into the phosphate glasses, it automatically reduces the OH content, that is the water content. It should be hydroxyl content, OH bonds should be reduces. Whenever reduce the OH content, it automatically Prana energy will be increases. So in the presence of lead oxide or lead fluoride may bring some advantages. So here they are bringing some important advantages to the spectroscopic and the anti-devitrifying properties of phosphate glasses. Moreover, the addition of lead fluoride, whenever adding the lead fluoride into the phosphate glasses, the worst phonon energy thereby suppress the non-radiative. Whenever adding the lead fluoride content into the phosphate based glasses, it automatically decrease the phonon energy and at the same time it suppress the non-radiative decay losses. So whenever the non-radiative decay losses is reduces, automatically emission cross section should be increases. That is the important parameter. So low phonon energy also very important input. Whenever the low phonon energy glasses useful for the high emission cross section, high emission properties, we can achieve the high emission cross section whenever using the low phonon energy glass systems. So phosphate glass also whenever adding with the fluoride content. Suppose the heavy metal oxide, lead fluoride, we are adding the phosphate glass, automatically post phonon energy will be decreases. At the same time, non-radiative decay losses also decreases. Same time, it will enhance the emission cross section. Emission properties will be increases. These are the one of the important advantage for the phosphate glasses. Next, coming to the phosphate glasses, properties of phosphate glasses. The glass former compared in phosphate glasses P2O5, pure phosphate glasses P2O5 has a melting point of 560 degrees centigrade. So pure phosphate glasses P2O5 is melting point is 560 degrees centigrade. At the same time, boiling point is 605 degrees centigrade. These are the phosphate glasses, pure phosphate P2O5 phosphate glass melting point. At the same time, boiling point is 605 degrees centigrade. Some of the properties for the pure phosphate glass system. Pure means P2O5 phosphorus pentoxide. So extraordinary refractive index N value is having the high refractive index value. That is extraordinary refractive index. N value is 1.4930. Whenever the yellow wavelength, that is 5491 nanometer. Whenever sodium lamp is used as a active source, whenever measuring the refractive index at that time, at the wavelength of sodium wavelength, the refractive index value should be 1.4930. These are the very important extraordinary refractive index of the phosphate classes. Next one, thermal expansion coefficient alpha value is 13.7 into 10 power minus 6 per degree centigrade, and the thermo-optic coefficient dN by dt value is minus 92.9 into 10 power minus 6 degree centigrade. These are the thermo-optical coefficient value dN by dt. Next, hypothetically, the phosphorus pentoxide has a UV edge of less than 150 nanometer. That means that the energy value is around 8.27 electron volt. So UV range, this is UV range less than 150 nanometers. However, phosphorus pentoxide generally contains water which shifts the edge towards longer wavelength. So this is mainly because of the water content in our phosphorus pentoxide glasses having the some water content. That is why that wavelength shift the edge towards longer wavelength. That is why its wavelength should be less than 150 nanometer and the energy is 8.27 electron volt. These are the important properties of the pure phosphate glasses P2O5. Next, properties of phosphate glass. Phosphate glasses are technologically and biologically important materials as they generally have a higher thermal expansion coefficient. It's having higher thermal expansion coefficient alpha and lower glass transition temperature Tg. It's having the glass transition temperature will be lower Tg value and compared to silicate and borate glasses, where alkali and alkaline earth can be added to modify the properties. Whenever if you are adding the alkaline and alkaline earth metals into the phosphate based glass, we can tune these two parameters, thermal expansion coefficient at the same time lower glass transition temperature, if you are comparing to silicate and borate glasses. There is also a great interest in alkaline earth phosphate glasses due to their high transparency for UV light. Whenever in ultraviolet region also you are having the high transparency, not only visible region and infrared region, in the UV region also it looks like a highly transparency because it's having the one of the important property for the phosphate glasses. Next, the structure of the glass determines its optical, thermal and chemical properties. The basic building blocks of the crystalline and amorphous phosphate are the P-phosphate tetrahedral, which link via converts the bridging oxygens to form the various phosphate anions. This is the how crystal structure into the phosphate glasses. It determines the optical, thermal and chemical properties. So in this phosphate glass we can study the how structure is looks like. Next, these are the structure of the phosphate glass. See, if this diagram shows here Q3, Q2, Q1, Q0. That is nothing but a basic phosphate tetrahedral sites. Here Q3. See, phosphorus surrounded by the oxygen ions. So O minus, this is cation. O plus means this is positive anions. These anions. So here only one cation surrounded by the three anions oxygens. That is why this says a Q3. So 3 anions oxygens are coordinated with phosphorus. Next here see Q2. Q2 is nothing but here see minus O minus O minus. This is 2 cations at the same time 2 anions. That is why Q2. Only we can mention the QC. Using the describe the QI is terminology where the I represents the number of bridging oxygens per tetrahedral as shown in the schematic diagram. So here Q3 means here 3 oxygen anions. That is why Q3. Here 2 oxygen anions. That is Q2. Here only O minus, O minus, O minus. Only one is there. Only one anion of the oxygen will be linked with phosphorus. So that is a Q1. Here see O minus, O minus, O minus. All are cations will be linked with phosphorus. But no anions here. That is why Q0. Q0 is nothing but this is bridging of oxygens per tetrahedral site. That is here nothing. So no anions is present here in this case. That is why Q0. Here only one oxygen anion will be linked with phosphorus. That is Q1. Here 2 anions. That is Q2. Here 3 anions. That is Q3. These are the tetrahedral units can be classified using the Q-site model. Proposal by Limpa et al. He discovered this kind of proposal Q3, Q2, Q1, Q0 sites. Although the model was initially used to describe the structure of binary silicate glasses. It can also be applied to phosphate glass systems also. So based on this model, phosphate anions can be described using the 2A terminology, where I represents the number of bridging oxygens per tetrahedron as shown in the schematic diagram. So in this system, you can know the how bridging oxygen will be shared to the phosphates. Next, this is structural properties of the phosphate glasses. This table shows the oxygen to phosphate ratio for variety of phosphate glasses. Here, different kind of phosphate glasses. This is a present network. This is O by P means oxygen phosphorus ratio. First one is ultra phosphate glasses. That oxygen phosphorus ratio should be less than equal to 3. As phosphate glasses around 3.0. Next is polyphosphate glasses classified into two types. One is pyrophosphate glass, the other one is orthophosphate glass. This oxygen phosphorus ratio, it should be value in the range of 3.5. The orthophosphate is 4.0. The phosphate glass networks can be classified by the oxygen phosphate ratios, which describe the tetrahedral linkage via bridging oxygens between neighboring phosphorus tetrahedral as summarized in table 1. These are the different phosphate based glasses and its oxygen phosphorus ratios. In the case of ultra phosphate glasses, it's having the value is oxygen phosphorus ratio should be less than 3.0. If you pure phosphate glasses, the oxygen phosphorus ratio should be 3.0. Pyrophosphate glasses, that value is 3.5. And orthophosphate glass oxygen phosphorus ratio will be in the order of 4.0. So these are the different kind of phosphate glasses that oxygen phosphorus ratios. Next, structure of phosphate glasses. The addition of modifying metal oxides depolymerize the network structure by converting bridging oxygens PO links and non-bridging oxygen resulting PO and metal oxide links, and in the process forming an ultra phosphate network that should be 2.5 less than equal to 2.5, that the oxygen phosphorus are at the same time less than 3.0. This is dominated by the 2,3 tetrahedral system. Further increase in the modifier content result in the polyphosphate composition, oxygen phosphorus ratio greater than 3.0. Based on Q2 chain terminology, by Q1 tetrahedral where be the average chain length are shorter than that of the metaphosphate compositions. These are the different kind of composition, how that oxygen phosphorus ratio should be in the order. And the pyrophosphate stoichiometry oxygen phosphorus ratio will be equal to 3.5. The network is dominated by phosphate domains Q1 minus Q1, while at the orthophosphate stoichiometry oxygen phosphorus ratio will be in the order of 4.0. The glasses contains isolated whenever the Q0 tetrahedral will be present in the phosphate structures. Next, coming to the structural properties of the phosphate glasses. The structural phosphate glasses, mainly the following steps shows the depolymerization of metaphosphate with the addition of alkali earth oxides and fluorides. Whenever they present in the phosphate glasses, alkali or alkali earth oxide as well as fluorides. And that is how this structure will be looks like. So first one is addition of alkali or alkali earth oxide such as sodium oxide or calcium oxide is added into the phosphorus pentoxide P2O5 glass, resulting in the conversion of three-dimensional network of linear phosphate chains. This is the linear phosphate chain. See, phosphorus, we are adding of sodium oxide Na2O or calcium oxide. These are the alkali or alkali earth oxide. Whenever added into the phosphate glasses, the chain structure will be looks like this. Oxygens, the phosphorus. So each phosphorus surrounded by the 4 oxygens. Here, these are the 3 anions. Here also 3 anions. The 3 anions. A 2-3 system. This is the one of the depolymerization metaphosphate glass structure system. Next, second one is this linear chain structure result in cleavage of phosphorus oxygen phosphor linkage and the creation of non-bridging oxygens in the glass. Calcium ions can serve as ionic cross links between the non-bridging oxygens of 2 different chains. These are the 2 different chains whenever adding with calcium oxide, the calcium 2 plus. These are the phosphorus linked with 4 oxygen. This phosphorus linked with 4 oxygen, 1 cation, remaining 3 are the anions. So here in this case, here is 2 are the cations, 2 anions, here 0. That means anions is 4. That is Q4. These are the different kind of structures of the phosphate classes. Next, third one is the with increasing amount of fluoride. Whenever the adding with the fluoride content in the phosphorus pentoxide, the chain became shorter and shorter. Take the alkali or alkali earth oxide, alkali earth fluorides as an example. The process is as follows. So whenever adding the alkali earth fluorides, RF is added into the phosphorus structure, you can see the different kind of structure, that is the metaphosphate network are continuously disturbed and phosphorus fluoride groups are gradually formed. This is like a chain. Next, coming to the fourth one, this is fluorophosphate glass where fluoride, metal fluoride or fluoride is added into the aluminum oxide, magnesium oxide, and lithium oxide can also form the aluminum fluorides, magnesium fluorides, lithium fluorides. These are the different kind of alkali or alkali earth oxide whenever added into the phosphate based glasses. At that time, it can form the tetrahedral and then reconnect the disrupted chains to one another so that the stability of glass formation and chemical durability are increased. Take aluminum fluoride as an example. The above process can be expressed as follows. These are the different whenever adding the aluminum oxide or magnesium oxide or lithium oxide. This is the form of fluoride contents. So that is aluminum fluoride or magnesium fluoride or lithium fluoride. At that time, its structure will be looks like in this form. This is when a phosphorus chain. This is a phosphorus. Whenever adding with the metal oxides, fluorides, aluminum fluoride or magnesium fluoride or lithium fluoride, whenever adding to the fluoride content in the phosphate glasses, it converted into the different kind of chains like this. These are the structural properties of the phosphate glasses. So these are the cited by the different kind of citations by used in this outline of the today talk. So thank you. We will be continuing in the next session. So next session we are discuss about the different type of oxide based glass systems, that is the silicate glasses, diluted glasses, gel made glasses. Thank you once again.
Like, share and subscribe. Hit the bell icon for more updates.